The farthest major planet in the solar system should be the quietest. It sits 4.5 billion kilometers from the Sun, bathed in less than 0.1% of the light that reaches Earth. Its cloud top temperature plunges to minus 210 degrees Celsius. Every intuition says this world should be frozen still, a cold blue marble drifting in permanent silence at the edge of everything. It is not. Neptune screams with winds that exceed 1,200 miles per hour, the fastest ever recorded on any planet. It generates Earth-sized storms that appear, rage, and vanish within years. It radiates more than twice the energy it receives from the Sun. One of the coldest giants in the solar system is also one of its most violently unstable. If you enjoy having your assumptions about the universe completely destroyed, do me a favor and hit that like button and subscribe. It genuinely helps this channel keep bringing you stories like this one, and I appreciate every single one of you. Let's begin. There is a rule that seems so obvious it barely needs stating. The farther you travel from a fire, the colder you become. Stand beside a campfire and the heat presses against your skin. Step back 10 paces and the warmth fades. Walk 100 meters into the dark and you feel nothing at all. The fire still burns, but its influence has abandoned you. Every human being understands this without being told. It is written into the deep logic of how energy behaves. Heat radiates outward, distance weakens it. Eventually, it vanishes. The solar system obeys the same principle on a scale so enormous it stops feeling real. At the center sits the Sun, a thermonuclear furnace converting 4 million tons of hydrogen into energy every second, burning at 15 million degrees at its core, radiating power outward in every direction at the speed of light. That radiation is the engine behind nearly everything that moves, grows, and changes on every world it touches. Mercury, the closest planet, receives roughly 7 times more solar energy per square meter than Earth does. Its dayside surface reaches 430 degrees Celsius, hot enough to melt lead. Venus, wrapped in a suffocating blanket of carbon dioxide, traps so much solar energy that its surface sits at 460 degrees, hotter even than Mercury despite being farther away. Earth, orbiting at 150 million kilometers, receives the exact amount of energy needed to sustain liquid water, weather systems, and a biosphere. Mars, 1.5 times farther out, gets less than half of Earth's solar input. Its average surface temperature drops to minus 60 degrees Celsius. The deserts of Mars are frozen wastelands compared to the deserts of Earth, and the only difference is distance. Now keep going, cross the asteroid belt, reach Jupiter, 5 times farther from the Sun than Earth. The solar energy arriving at Jupiter drops to roughly 4% of what Earth receives. That is a staggering reduction. If you stood on a hypothetical surface at Jupiter's cloud tops, the Sun would still be the brightest object in the sky, but it would appear noticeably smaller than it does from Earth. The warmth it provides would be negligible compared to what Jupiter generates from its own interior. Move farther still. Saturn orbits at roughly 10 times Earth's distance. It receives barely 1% of Earth's solar energy. The Sun from Saturn looks like a brilliant point of light, still unmistakably the brightest star in the sky, but its ability to heat anything at that range has diminished to almost nothing meaningful for driving large-scale atmospheric phenomena on its own. Uranus sits at roughly 20 times Earth's distance from the Sun. Neptune orbits at approximately 30 times Earth's distance. At Neptune, the solar energy arriving per square meter is roughly 900 times weaker than what Earth receives. Think about that number for a moment. 900 times less energy. If you could somehow stand in Neptune's upper atmosphere and look back toward the Sun, you would see a sharp, brilliant point of light, far brighter than any star in Earth's night sky, but no longer the blazing disk that dominates our daytime experience. The Sun from Neptune is a distant beacon, not a furnace. Its light takes over 4 hours to make the journey, and the energy it delivers to Neptune's cloud tops is so feeble that it amounts to approximately 1.5 watts per square meter. For comparison, Earth receives about 1,361 watts per square meter at the top of its atmosphere. Neptune gets roughly 1/900th of that. This gradient is the most basic organizing principle of the solar system. Closer means warmer, more energetic, more active. Farther means colder, less energetic, less active. It governs the surface temperatures of rocky worlds, the chemistry of planetary atmospheres, the rates of geological and meteorological processes, and it creates a powerful expectation that seems almost impossible to violate. The farthest major planet from the Sun should be the quietest. It should be the most thermally inert, the most meteorologically passive, the most atmospherically still. It should be a world where very little happens, because very little energy arrives to make anything happen. This is the assumption that Neptune was supposed to confirm. Before 1989, almost nothing was known about Neptune in any real observational detail. The planet had been discovered in 1846 through mathematics rather than direct observation. Astronomers had noticed that Uranus was not following its predicted orbital path. Something massive and unseen was pulling on it from farther out. The French mathematician Urbain Le Verrier calculated where the unseen planet must be, and the German astronomer Johann Galle found it within 1 degree of the predicted position on the very first night he looked. The discovery was a triumph of Newtonian mechanics. But finding Neptune and understanding Neptune were two entirely different achievements separated by more than a century. From Earth, Neptune is extraordinarily difficult to observe. At an average distance of 4.5 billion kilometers, it appears as a tiny disk even in the largest ground-based telescopes. Its angular diameter in the sky is roughly 2 arcseconds, which is about the size of a coin viewed from 3 kilometers away. Resolving any surface detail from Earth requires exceptional atmospheric conditions or advanced adaptive optics. For most of the 20th century, astronomers knew only the most basic facts about Neptune. They knew its orbital period, roughly 165 Earth years. They knew its approximate size, about 4 times Earth's diameter. They knew its mass, roughly 17 times Earth's mass. They knew its atmosphere contained hydrogen, helium, and methane, with the methane absorbing red light and giving the planet its distinctive blue colour. And they knew it was very, very cold. The expected surface temperature at Neptune's distance from the Sun, based purely on solar energy input, would be approximately minus 228 degrees Celsius. The measured effective temperature is somewhat warmer than this, around minus 214 degrees Celsius, but still brutally cold by any standard. These are temperatures where methane freezes, where ammonia solidifies, where the chemistry of the atmosphere slows to a crawl. Every thermodynamic principle says that a world this cold and this starved of external energy should exhibit minimal atmospheric activity. There simply is not enough available energy to drive powerful weather systems. This expectation was reinforced by what astronomers observed closer to home. Weather on Earth is ultimately driven by solar heating. The sun warms the equator more than the poles, creating temperature gradients that drive atmospheric circulation. Warm air rises, cool air sinks, pressure differences create winds, and the whole system generates the storms, jet streams, and weather patterns that define our planet's climate. Remove the sun and Earth's atmosphere would eventually settle into thermal equilibrium. The winds would stop, the storms would die, the weather would cease. The same basic principle applies throughout the solar system. Jupiter has spectacular weather, including the Great Red Spot, a storm system larger than Earth that has persisted for centuries. But Jupiter is enormous, more than 1,300 times Earth's volume, and it sits close enough to the Sun to receive meaningful solar energy. More importantly, Jupiter radiates approximately 1.7 times more heat than it absorbs from the Sun, meaning it has a powerful internal energy source supplementing the solar input. Jupiter's weather makes sense. The combination of massive size, residual internal heat, and moderate solar energy provides more than enough power to drive spectacular atmospheric dynamics. Saturn tells a similar story. It is farther from the Sun than Jupiter, but still receives enough combined energy from solar and internal sources to generate impressive weather, including a bizarre hexagonal jet stream at its north pole and occasional massive storm eruptions that can encircle the entire planet. Saturn radiates about 1.8 times more energy than it receives from the Sun. Its atmospheric violence is explicable within the framework of energy-driven meteorology. Uranus complicates the picture in one particular way, but ultimately reinforces the expectation about Neptune. Uranus orbits at roughly 20 times Earth's distance from the Sun, and its atmosphere appeared remarkably bland when Voyager 2 flew past it in January 1986. The spacecraft's cameras captured a nearly featureless blue-green globe with almost no visible cloud structure. Uranus appeared calm, quiet, and meteorologically dead. The Voyager 2 encounter with Uranus in January 1986 had been one of the most anticipated planetary flybys of the decade, and in atmospheric terms, it delivered an answer so definitive it bordered on anticlimactic. As the spacecraft closed in on the blue-green ice giant, the imaging team expected to find at least some cloud structure. Jupiter had its bands and its great red spot. Saturn had its subtle but detectable belts and zones. Surely Uranus, a world 14.5 times Earth's mass with a substantial hydrogen-helium atmosphere, would show something. It showed almost nothing. The highest resolution images returned a globe so featureless that some scientists initially suspected the camera filters were washing out the contrast. They were not. Uranus genuinely lacked prominent cloud features at the wavelengths Voyager could observe. A handful of faint cloud bands were eventually extracted through aggressive image processing, and a few small discrete cloud features were detected near the planet's south pole, but these were so subtle that they would have been invisible in any less meticulously processed dataset. Compared to the rich atmospheric tapestry of Jupiter, or even the delicate banding of Saturn, Uranus looked blank, smooth, inert, as if someone had taken a giant planet and simply switched off its weather. The scientific community absorbed this result and drew what seemed like the obvious conclusion. The distance rule held. Uranus sat 20 times farther from the Sun than Earth, received roughly 1/400th of Earth's solar energy, and lacked sufficient internal heat to compensate. The result was atmospheric stillness. The energy simply was not there to drive significant weather. And if Uranus, at 20 times Earth's solar distance, was this quiet, then Neptune, at 30 times Earth's solar distance, receiving even less of the Sun's already feeble radiation at that range, should be quieter still. Some planetary scientists went further, suggesting privately that the Neptune flyby might prove to be the least visually interesting of Voyager 2's entire grand tour. The planet was expected to deliver important data about magnetic fields, ring structures, and the captured moon Triton, but the atmosphere itself was written off as a probable repeat of the Uranus experience. Another bland ice giant, another smooth blue disk, another confirmation that the outer solar system was where atmospheric activity went to sleep. This prediction felt safe. It felt conservative. It was grounded in the freshest observational evidence available, direct measurements from a spacecraft that had just visited the nearest comparable world. It represented the best thinking of the best planetary scientists in the world, informed by real data from a real flyby, and 3 years later, Neptune would prove every single element of it spectacularly, comprehensively, and almost embarrassingly wrong. Uranus was far from the Sun, it was cold, and its atmosphere was accordingly still. Scientists measured that Uranus radiates almost no more energy than it receives from the Sun, putting its energy balance ratio at approximately 1.06. Something about Uranus's interior appeared to trap or fail to generate significant excess heat, possibly as a result of a catastrophic ancient collision that may have tipped the planet onto its side and disrupted its internal heat transport. The result was an atmosphere with very little energy to drive weather. Uranus looked exactly like what you would expect from a cold, distant, energy-starved world, and so the logical progression seemed airtight. Mercury is scorched. Venus is suffocated in heat. Earth has moderate weather driven by moderate solar input. Mars is cold and largely still. Jupiter is massive and internally heated, producing tremendous weather. Saturn is similar but slightly calmer. Uranus is far, cold, and meteorologically dead. Neptune, even farther, even colder, receiving even less sunlight, should be the quietest of them all. The edge of the solar system should be where atmospheric activity goes to die. This was the prevailing assumption when Voyager 2 began its approach to Neptune in the summer of 1989. Voyager 2 is one of the most remarkable machines humanity has ever built. Launched on the 20th of August, 1977, it was designed to exploit a rare planetary alignment that occurs roughly once every 175 years, allowing a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune in sequence using gravitational slingshots. By the time it reached Neptune, Voyager 2 had been flying for 12 years. It had already transformed our understanding of Jupiter's volcanic moon Io, Saturn's complex ring system, and Uranus's bizarre tilted magnetosphere. Neptune was the final target, the last major planet, the end of the Grand Tour. The encounter was not expected to produce dramatic results. Scientists anticipated confirming what they already suspected, that Neptune was a cold, distant world with a relatively quiet atmosphere, perhaps showing a few faint cloud bands similar to Uranus. The planet was so far from the Sun and so poorly understood that expectations were deliberately kept modest. Some researchers hoped to detect methane clouds. Others wanted to study Neptune's magnetic field or examine its rings, which had been tentatively detected from Earth. But atmospheric fireworks were not on anyone's prediction list. To understand why Neptune's atmosphere was expected to be calm, it helps to understand what Neptune actually is in physical terms. Neptune is classified as an ice giant, a designation it shares only with Uranus. This makes it fundamentally different from Jupiter and Saturn, which are gas giants. The distinction matters because internal structure determines how a planet stores, transports, and releases energy, which in turn determines what its atmosphere can do. Jupiter and Saturn are dominated by hydrogen and helium. Their interiors consist primarily of molecular hydrogen in the outer layers, transitioning to metallic hydrogen under immense pressure deeper inside. They are essentially enormous balls of the lightest elements in the universe, compressed by their own gravity into layered structures that generate and transport heat efficiently. Their sheer mass, 318 Earth masses for Jupiter, 95 for Saturn, creates gravitational compression significant enough to maintain powerful internal heat sources billions of years after formation. Neptune is built differently. Its mass is only about 17 times that of Earth. Its interior is thought to consist of a relatively small rocky core, perhaps 1 to 1.5 Earth masses, surrounded by a thick mantle of hot, dense ices. The term ices here is misleading. At the pressures and temperatures inside Neptune, water, methane, and ammonia do not exist as familiar frozen solids. They exist in exotic high-pressure states, compressed into superheated fluids or superionic phases where oxygen atoms form a crystalline lattice, while hydrogen ions flow freely through it like a liquid. Neptune's interior is not a frozen world. It is a crushing furnace of compressed volatiles under pressures millions of times greater than Earth's atmospheric pressure. But this interior is wrapped in a relatively thin hydrogen-helium atmosphere that represents only the outermost skin of the planet. This atmospheric envelope is what we observe. When we look at Neptune through a telescope, we see only the top of this hydrogen-helium layer, tinted blue by the presence of methane, which absorbs red wavelengths of light and reflects blue ones back into space. The blue color is striking, giving Neptune an appearance of serene beauty that reinforces the expectation of calmness. From Earth, Neptune looks peaceful, tranquil, almost inviting, in the way that a deep, still ocean looks inviting from a great height. But that appearance is a lie. The methane that makes Neptune blue also plays a role in its atmospheric chemistry that scientists are still working to fully understand. Methane absorbs not only visible red light but also infrared radiation, acting as a greenhouse component that can trap and redistribute heat within the atmosphere. The interactions between methane, hydrogen, and trace compounds at different altitudes create layered structures of hazes and clouds that respond to both solar ultraviolet radiation and internal thermal energy in complex ways. The blue color is not simply a cosmetic detail. It is a signature of a chemically active atmosphere where methane is being processed, broken apart by ultraviolet light in the upper layers, and reformed into more complex hydrocarbons that contribute to the hazes observed at various altitudes. Neptune's physical dimensions add to the impression of a substantial but unremarkable world. Its equatorial diameter is approximately 49,500 kilometers, making it nearly 4 times wider than Earth. Its volume could contain 57 Earths, yet by giant planet standards, Neptune is modest. Jupiter could swallow more than 1,300 Earths. Saturn could accommodate 764. Neptune is the smallest of the 4 giant planets, the least massive, the least gravitationally dominant. In every obvious metric, Neptune is the runt of the giant planet family, sitting at the far edge of the Sun's influence, receiving almost no warmth, built from exotic ices rather than the lighter hydrogen that fills Jupiter and Saturn. Everything about this profile screams quiet. Consider the full picture as it would have appeared to a planetary scientist in 1988, 1 year before the Voyager 2 encounter. You have a planet 30 times farther from the Sun than Earth. It receives less than 1/900th of Earth's solar energy. Its nearest sibling, Uranus, proved to have an almost featureless atmosphere when visited 3 years earlier. Neptune is even farther out, even colder, and has roughly similar mass and composition to Uranus. The logical prediction is straightforward. Neptune should be calm, perhaps even calmer than Uranus, since it receives even less solar energy. The atmosphere should show faint banding at best, possibly some diffuse cloud features, but nothing dramatic. Certainly nothing violent. Certainly nothing that would rival the atmospheric spectacles of Jupiter or Saturn. This prediction was reasonable. It was logical. It was supported by every principle of energy-driven meteorology. And it was completely, spectacularly, and almost absurdly wrong. Voyager 2 made its closest approach to Neptune on the 25th of August, 1989, passing within approximately 4,950 kilometers of the planet's cloud tops. The images that came back across the full breadth of the outer solar system did not show a quiet world. They did not show a featureless blue globe like Uranus. They did not confirm the expectation that the farthest major planet should be the most atmospherically still. Instead, they showed chaos. The first and most dramatic feature was a massive dark oval in the southern hemisphere, roughly 13,000 kilometers long and 6,600 kilometers wide. It was approximately the same size as Earth. Scientists named it the Great Dark Spot, a deliberate echo of Jupiter's Great Red Spot, because the comparison was irresistible. Here was a storm system on the farthest major planet that rivaled the most famous atmospheric feature on the largest planet. The Great Dark Spot was an anticyclonic vortex, rotating counterclockwise, drifting westward through Neptune's atmosphere, accompanied by bright white clouds of methane ice that formed along its edges where air was forced upward and cooled. But the Great Dark Spot was only the beginning of what Voyager 2 revealed. A second, smaller dark spot was detected farther south, nicknamed Dark Spot 2. Between the two storms, an incredibly fast-moving bright cloud feature was observed racing around the planet, completing a full circuit every roughly 16 hours. Scientists nicknamed it the Scooter because of its remarkable speed relative to surrounding atmospheric features. And then there were the winds. The wind measurements that came back from Voyager 2 did not just surprise scientists, they stunned them. Neptune's atmosphere was moving at velocities that had no right to exist on a world this cold, this distant, and this starved of sunlight. The winds were extraordinary at every latitude. The equatorial jet blew retrograde, against the direction of the planet's rotation, at roughly 900 miles per hour. At higher latitudes, prograde winds raced even faster, exceeding 1,200 miles per hour. These were not gusts. These were sustained, planet-girdling jet streams of a ferocity that exceeded anything measured on Jupiter or Saturn. The farthest major planet from the Sun was producing atmospheric velocities that no other world could match. Everything scientists thought they understood about the relationship between distance, energy, and atmospheric activity collapsed in the space of a single planetary flyby. Neptune was not quiet. Neptune was not still. Neptune was not the peaceful, frozen endpoint that the outer solar system was supposed to deliver. It was violent, profoundly, physically, measurably violent. And the violence was not subtle. It was not marginal. It was not a few percent more active than expected. Neptune's atmospheric fury exceeded that of Jupiter, a planet roughly 6 times closer to the Sun with nearly 19 times more mass. Something was terribly, beautifully wrong with the assumption that distance should bring silence. And what comes next reveals exactly how violent Neptune truly is, feature by feature, storm by storm, in an atmosphere that has no business behaving this way. When Voyager 2's images arrived at the Jet Propulsion Laboratory in Pasadena during the summer of 1989, the reaction among planetary scientists was not merely surprise, it was disorientation. The data coming back from 4.5 billion kilometers away did not just exceed expectations, it inverted them. The atmosphere of Neptune was not behaving according to any model that placed solar energy as the primary driver of planetary weather. It was behaving as though an entirely different set of rules governed the outer solar system, rules that nobody had properly accounted for, rules that made the farthest giant planet one of the most meteorologically ferocious worlds ever observed. The encounter had been building for 12 years. Voyager 2, launched in 1977, carrying instruments designed and calibrated before most of the scientists who would interpret the data had finished graduate school. By the time the spacecraft reached Neptune, its primary radio receiver had failed, its scan platform had seized during the Saturn encounter and required careful reprogramming, and the signals it sent back to Earth took over 4 hours to arrive, weakened by distance to a whisper barely distinguishable from cosmic background noise. The deep space network antennas that received those signals had to be linked together across multiple continents to capture enough photons to reconstruct the images. Everything about the encounter was operating at the ragged edge of what 1970s engineering could sustain across interplanetary distances that dwarfed every previous mission. At the Jet Propulsion Laboratory in Pasadena, the imaging team led by Bradford Smith had spent months preparing for the flyby window. The closest approach would last only hours. Neptune rotates once every approximately 16 hours, so the spacecraft would see roughly half the planet in sharp detail before racing past and leaving Neptune's gravitational sphere forever. Every minute of imaging time was scheduled with precision, every camera angle calculated to maximize coverage of a world no human instrument had ever resolved. The first high-resolution frames began arriving in early August 1989 as Voyager 2 closed the distance. Initial images showed a blue disk, as expected, with the methane-colored atmosphere giving the planet its characteristic hue. But as the resolution sharpened over the following days, features began appearing that had no business being there. Bright white streaks of cloud, dark oval structures embedded in the blue background, banding that suggested powerful organized wind flows. With each successive image, the atmosphere revealed more complexity, more structure, more activity. By the time the closest approach images arrived on the 25th of August, the room at JPL understood that every prediction about Neptune's atmospheric quiescence had been wrong. The screens showed a world in full atmospheric fury, and the data that followed would confirm the visual impression, with hard numbers that shocked the planetary science community. The wind measurements were the first and most devastating blow to conventional thinking. Voyager 2's instruments tracked cloud features at various latitudes, measuring their displacement over time to calculate wind velocities relative to Neptune's interior rotation rate. The interior rotation had been determined through radio emissions generated by Neptune's magnetic field, giving scientists a fixed reference frame against which atmospheric motion could be measured. What the data revealed was extraordinary. At the equator, Neptune's winds blow retrograde, meaning they travel in the opposite direction to the planet's rotation. This alone is unusual. On Jupiter and Saturn, equatorial winds blow prograde, racing ahead of the planet's spin in the same direction it rotates. Neptune reverses this pattern. Its equatorial jet stream pushes westward against the planet's eastward rotation at sustained speeds reaching approximately 1,400 kilometers per hour. At higher latitudes, the wind direction reverses, blowing prograde and reaching even greater velocities. Near the latitudes where the Great Dark Spot was observed, winds approached 2,100 kilometers per hour, or roughly 1,300 miles per hour relative to the interior. These numbers need context to feel real. The most powerful sustained surface winds ever recorded in a tropical cyclone on Earth reached approximately 215 miles per hour, a record set by Hurricane Patricia in 2015. Those winds are catastrophic. They flatten reinforced concrete structures, they strip bark from trees, they turn automobiles into tumbling projectiles. They represent the absolute ceiling of what solar-driven weather can produce on a rocky planet with oceans and continents and a relatively thin atmosphere heated to habitable temperatures, Neptune's sustained winds are roughly 6 times faster than the worst hurricane Earth has ever produced. If winds of this magnitude somehow occurred at sea level on our planet, they would exceed the speed of sound in air at standard conditions. Objects caught in such a flow would experience aerodynamic forces beyond anything terrestrial engineering is designed to withstand. But the comparison is even more jarring when you consider the energy budgets involved. Earth's hurricanes are powered by warm tropical oceans heated by direct, intense sunlight. Neptune receives almost no sunlight by comparison. Its atmosphere is 200 degrees below zero. The energy available to drive weather on Neptune is a tiny fraction of what drives weather on Earth. And yet Neptune's winds are 5 times stronger. This is not a minor discrepancy. This is not a case of Neptune being slightly more active than predicted. This is a world where atmospheric velocities defy the most basic energy accounting that planetary science relies upon. Something is powering those winds that has almost nothing to do with the Sun. The wind pattern across Neptune's disk reveals a structured, organized system rather than random turbulence. Like Jupiter and Saturn, Neptune's atmosphere is divided into alternating bands of latitude where winds blow in different directions. The equatorial zone features the powerful retrograde jet. Moving toward the poles, the wind direction shifts to prograde, with the fastest prograde winds occurring at mid-latitudes in both hemispheres. This banded structure indicates that Neptune's atmospheric circulation is driven by deep, persistent forces rather than transient surface phenomena. The winds are not gusts or squalls. They are permanent features of the planet's atmospheric architecture, maintained continuously despite the negligible solar heating available to sustain them. The organization of these wind bands also differs from Jupiter and Saturn in ways that reveal Neptune's unique atmospheric dynamics. Jupiter has dozens of narrow alternating bands visible in its cloud structure. Saturn has fewer but still multiple distinct bands. Neptune has a much simpler pattern with broader latitudinal zones and fewer distinct jet streams. This simplicity might seem to suggest a less active atmosphere, but the opposite is true. The fewer, broader jets concentrate atmospheric energy into larger-scale flows, producing the extraordinary velocities observed. The atmosphere is not dissipating its energy across many small features. It is channeling it into a few massive rivers of wind that circle the entire planet at staggering speed. But winds alone do not define atmospheric violence. Storms do, and Neptune produces storms of a character and behavior unlike anything observed elsewhere in the solar system. The Great Dark Spot discovered by Voyager 2 was the first major storm system ever observed on Neptune, and it immediately challenged scientists' understanding of how giant planet storms work. It was an anticyclonic vortex, meaning it rotated in the direction opposite to what a low-pressure cyclone would produce in Neptune's southern hemisphere. High-altitude methane ice clouds formed bright white companions alongside the dark oval, condensing where atmospheric gases were forced upward along the vortex edges and cooled enough to crystallize. The storm drifted westward at roughly 300 meters per second relative to the surrounding atmosphere, and its shape oscillated over a period of approximately 8 days, with the oval stretching and compressing rhythmically as it interacted with the surrounding wind field. On Jupiter, the Great Red Spot has persisted for at least several centuries and possibly much longer. It is a stable, long-lived feature that has become synonymous with the planet itself. Scientists expected that if Neptune hosted a comparable storm, it might show similar longevity. The Great Dark Spot certainly looked comparable. It was roughly the same angular size relative to its host planet. It occupied a similar latitude range. It exhibited the same anticyclonic rotation. The parallel invited the assumption that Neptune had its own permanent atmospheric landmark. That assumption lasted exactly 5 years. When the Hubble Space Telescope turned its optics toward Neptune in 1994, the Great Dark Spot was gone, not diminished, not faded, gone. The storm that had been the most prominent atmospheric feature on the planet just 5 years earlier had vanished completely from the southern hemisphere. In its place, Hubble found a new dark spot in the northern hemisphere, as though Neptune had simply dissolved one storm and generated another in a different location. The smaller dark spot 2 observed by Voyager had also disappeared. This behavior was unprecedented. Jupiter's Great Red Spot is stable over human lifetimes and likely over centuries. Saturn's storms, while episodic, follow predictable patterns. But Neptune was generating massive vortex systems, sustaining them for a period of years and then destroying them entirely, only to produce new ones elsewhere on the planet. The atmosphere was not merely violent, it was unstable on a timescale that seemed almost reckless for a world receiving so little energy. Subsequent decades of Hubble monitoring have confirmed that this pattern is not an anomaly. It is Neptune's normal mode of operation. Multiple dark spots have been observed since the original Voyager encounter, each appearing in different hemispheres at different latitudes, persisting for a few years and then fading or vanishing. Based on the observational record accumulated over more than 30 years, astronomers now estimate that Neptune hosts a major dark vortex roughly half the time. The planet cycles through periods of spotted and unspotted appearance with a cadence that suggests continuous internal storm generation, balanced against dissipation mechanisms that destroy the vortices after relatively short lifetimes. One particularly striking episode occurred beginning in 2018, when Hubble detected a new dark storm in Neptune's northern hemisphere. This vortex, roughly 7,400 kilometers across, was observed drifting southward toward the equator over subsequent years. Models predicted that dark spots migrating toward the equator should dissipate, torn apart by the strong wind shear between the retrograde equatorial jet and the prograde mid-latitude flows. The storm appeared to be heading toward destruction. Then it did something no one expected. In observations taken in 2020, the storm reversed direction. It stopped its southward drift and began moving back toward the north, defying the predictions of every atmospheric model that had been applied to Neptunian vortex behavior. Even more remarkably, Hubble images revealed a second, smaller dark spot appearing near the larger one. Scientists proposed that this smaller feature might have been a fragment that broke away from the main vortex, a piece of the storm shearing off and drifting independently before dissipating. If confirmed, this would represent the first direct observation of a dark spot disruption process on Neptune, a phenomenon that computer simulations had predicted, but that had never been witnessed in real data. The fragmentation event was significant not merely because it was new, but because it offered the first real-time observational window into how Neptunian dark spots die. For decades, the only data scientists had was the appearance and disappearance itself. A storm would be detected in one set of Hubble observations and absent in the next, taken months later. The interval between observations was too coarse to capture the actual destruction process. Did the vortices simply dissipate, spreading their energy into the surrounding atmosphere until they became undetectable? Did they migrate to latitudes where wind shear tore them apart? Did they collapse inward, or did they fragment outward? Computer models generated all of these possibilities, but the observational record could not distinguish between them. The 2018 storm, by being caught in the act of both reversing direction and shedding a fragment, provided the first direct evidence that at least some dark spots undergo active disruption rather than passive fading. The implications for atmospheric modelling are substantial. If dark spots routinely break apart rather than gently dissolving, the energy released during fragmentation could feed back into the surrounding atmosphere, potentially triggering new storm formation. Neptune's atmosphere might operate as a self-sustaining cycle of vortex creation and violent destruction, with the debris of one storm seeding the conditions for the next. The observational picture expanded further in 2023, when a team led by Patrick Irwin at the University of Oxford achieved something previously thought impossible. Using the multi-unit spectroscopic Explorer instrument on the European Southern Observatory's Very Large Telescope in Chile, they detected a dark spot on Neptune from the ground. Every previous dark spot detection had required either the Voyager spacecraft at close range or the Hubble Space Telescope above the distorting effects of Earth's atmosphere. Ground-based telescopes lacked the resolution and contrast sensitivity to pick out these subtle dark features against Neptune's blue disk from 4.5 billion kilometers away. The VLT detection broke that barrier, and the spectroscopic data it provided revealed something Hubble's cameras alone could not. The dark region was not simply an absence of bright cloud material. The spectrum indicated that the dark appearance resulted from a darkening of the aerosol particles within the atmosphere at the storm's location, suggesting that the vortex was altering the chemical properties of the particles within it, not merely pushing clouds aside to reveal darker layers below. An unexpected bright companion spot detected alongside the dark vortex appeared to consist of a distinct deep cloud layer at a different atmospheric altitude than the methane ice clouds typically associated with dark spot companions. These spectroscopic details, unobtainable from Hubble's imaging cameras alone, hinted at a more complex vertical structure within the storms than previous models assumed. This episode captured something essential about Neptune's atmospheric character. The storms on this planet do not simply form and persist. They do not simply form and die. They form, evolve, migrate, reverse course, fragment, and regenerate in patterns that remain poorly understood despite decades of observation. Neptune's atmosphere is not a system in equilibrium. It is a system in constant upheaval, producing and destroying features on timescales that make it one of the most dynamically variable planetary atmospheres in the known solar system. The dark spots themselves present a scientific puzzle that goes beyond their behavior. Their precise physical nature is still debated. Unlike Jupiter's Great Red Spot, which is a well-characterized high-pressure anticyclone with clearly defined cloud structures, Neptune's dark spots are less well understood because they have only been observed remotely from Earth's vicinity. The leading interpretation is that they are vortices in the deeper atmosphere, regions where downwelling air clears away the methane haze that normally obscures deeper atmospheric layers, revealing darker material beneath. The bright companion clouds that accompany the spots are thought to form where the vortex forces air upward along its periphery, cooling methane gas until it condenses into bright ice crystals at higher altitudes. But the details remain uncertain. Ground-based observations using the European Southern Observatory's Very Large Telescope in 2023 provided the first Earth-based detection of a Neptunian dark spot, offering new spectroscopic data that suggested the dark regions involve a darkening of the aerosol layer rather than a simple clearing of clouds. The observations also revealed an unexpected bright companion feature adjacent to the dark spot, which appeared to consist of a separate, deeper layer of cloud material not previously identified. Each new observation adds complexity rather than clarity. Neptune's storms are yielding their secrets slowly, and every answer seems to generate additional questions. Beyond the dramatic dark spots, Neptune's atmosphere exhibits another form of variability that proved equally surprising. The planet's cloud cover itself undergoes dramatic changes on timescales that should not be possible for a world receiving so little solar energy. Beginning in 2019, astronomers monitoring Neptune through the Keck Observatory, the Hubble Space Telescope, and the Lick Observatory noticed something alarming. The clouds were disappearing, not gradually thinning over years or decades, but rapidly vanishing within months. By 2020, the mid-latitude cloud bands, that had been a consistent feature of Neptune's appearance for nearly 3 decades of modern observation, had almost completely evaporated. The planet that had always shown a dynamic patchwork of bright methane clouds looked nearly bare, stripped down to its smooth blue background, with only a persistent south polar cloud cap remaining. This dramatic transformation was documented in a study published in 2023 that analysed 29 years of Neptune observations, spanning from 1994 through 2022. The researchers found that Neptune's cloud activity followed a pattern that correlated not with Neptune's own incredibly long seasons, each of which lasts approximately 40 Earth years, but with the 11-year solar cycle. When the Sun's ultraviolet output increased during periods of heightened solar activity, Neptune's cloud cover increased roughly 2 years later. When solar ultraviolet output declined, the clouds faded. The correlation was striking and statistically robust across 2.5 complete solar cycles of observational data. This finding was deeply counterintuitive. Neptune operates on a solar energy budget so thin it barely registers against what the inner planets receive. The idea that subtle changes in ultraviolet radiation from a star 4.5 billion kilometers away could drive significant atmospheric transformations on such a distant world seemed almost absurd. Yet the data was clear. The leading hypothesis proposes that increased solar ultraviolet radiation triggers photochemical reactions in Neptune's upper atmosphere, breaking apart methane molecules and producing more complex hydrocarbons that serve as condensation nuclei for cloud formation at lower altitudes. When solar ultraviolet output drops, the photochemical production slows, fewer condensation nuclei form, and the clouds dissipate. The near-total disappearance of clouds by 2020 represented the most extreme low point in cloud activity ever recorded on Neptune. The planet looked genuinely different from the way it had appeared during the entire Hubble era. And yet, even in this stripped-down state, the underlying atmospheric dynamics persisted. The winds did not stop when the clouds vanished. The jet streams continued screaming around the planet at their extraordinary velocities. The clouds were visible traces of deeper atmospheric processes, and their disappearance did not mean those processes had ceased. It meant only that the visible markers had temporarily been removed, leaving the violence churning invisibly beneath a deceptively smooth blue exterior. The Hubble image sequences documenting this transformation are striking even to non-specialists. Side-by-side comparisons of Neptune from 2002 and 2020 show what appears to be two entirely different planets. The earlier image shows a vivid blue disk decorated with bright white cloud bands at mid-latitudes, bright spots dotting the southern hemisphere, and a conspicuous bright cap of cloud activity over the South Pole. The 2020 image shows a nearly uniform blue sphere, eerily smooth, with virtually all cloud structure erased, except for a faint residual glow at the South Pole. The transformation took less than 2 years. For a planet whose seasons last 4 decades and whose orbital period spans 165 Earth years, a change this dramatic over such a short interval was genuinely startling. The research team, led by Imke de Pater at the University of California, Berkeley, assembled their findings from a remarkable dataset spanning nearly 3 decades of continuous monitoring. They combined observations from the Keck Observatory's near-infrared camera, the Lick Observatory, and the Hubble Space Telescope, creating one of the longest continuous records of atmospheric change ever compiled for an outer planet. The correlation they discovered between Neptune's cloud abundance and the solar cycle was not a subtle statistical hint. It was a clear, repeating pattern visible across 2.5 complete solar cycles. Neptune appeared brightest and cloudiest around 2002, dimmed around 2007, brightened again around 2015, and then plunged to its dimmest state ever recorded by 2020. Each peak in cloud activity lagged behind the corresponding peak in solar ultraviolet output by approximately 2 years, a delay consistent with the time required for photochemical processes to convert increased ultraviolet radiation into the condensation nuclei that seed cloud formation deep in the atmosphere. The 2-year lag is itself a clue about the vertical depth at which the solar influence operates. Ultraviolet photons are absorbed high in Neptune's stratosphere, where they break apart methane molecules into reactive fragments. These fragments recombine into more complex hydrocarbons, ethane, acetylene, and other compounds, which gradually settle downward through the atmosphere over months and years. When they reach altitudes where temperatures and pressures permit condensation, they serve as seeds around which methane ice clouds can nucleate. The entire process is a chain reaction linking the Sun's activity to Neptune's visible appearance through a multi-year sequence of chemical and physical steps, each one occurring at a different altitude in the atmosphere. The fact that this chain operates at all on a world receiving almost no measurable fraction of Earth's sunlight speaks to the extraordinary sensitivity of Neptune's atmospheric chemistry. By mid-2023, observations indicated that clouds had begun returning, consistent with the predicted lag following the rising phase of solar cycle 25. Neptune was clothing itself again, reassembling the bright features that Hubble and ground-based telescopes had tracked for decades. But the episode revealed something profoundly important about Neptune's atmospheric character. This is a world where the entire visible appearance can transform dramatically within a few years, driven by interactions between internal atmospheric chemistry and the faintest whisper of solar influence from billions of kilometers away. The atmosphere is not just violent. It is responsive, reactive, and variable on timescales that make it one of the most changeable planetary atmospheres in the solar system. Taken together, the evidence paints a portrait of a world in perpetual atmospheric turmoil. The winds are the fastest measured on any planet. The storms form, evolve, reverse course, fragment, and regenerate in cycles lasting only years. The cloud cover can wax and wane dramatically in response to solar variations so subtle they should be undetectable at Neptune's distance. Every feature of Neptune's atmosphere speaks of a world operating at a level of meteorological intensity that no simple energy budget based on solar input can explain. And this is where the central mystery sharpens into its most uncomfortable form. Consider the energy available to drive all of this activity. Neptune receives a negligible fraction of the solar energy that reaches Earth. Earth receives roughly 1,360 watts per square meter. Earth uses that abundant energy to generate weather systems whose most extreme expressions, Category 5 hurricanes, produce maximum sustained winds of roughly 250 miles per hour. Neptune, operating on less than 1/900th of that energy input, produces sustained winds exceeding 1,300 miles per hour. The ratio of wind speed to available solar energy is not just unfavorable, it is grotesque. Neptune produces roughly 5 times the wind speed from roughly 900 times less solar energy. This is not a puzzle that better atmospheric modelling can resolve on its own. This is a fundamental energy crisis. The solar input at Neptune is so minimal that even if the atmosphere were perfectly efficient at converting every incoming photon into kinetic energy, which is physically impossible, the result would fall catastrophically short of explaining the observed wind speeds. The Sun simply cannot be the primary driver of Neptune's atmospheric violence. Something else must be providing the energy. Something internal. Something powerful enough to overwhelm the pathetic trickle of sunlight reaching the outer solar system and drive an atmosphere into a state of permanent, ferocious, relentless motion. When Voyager 2 measured Neptune's thermal emission, it confirmed what the atmospheric behavior already implied. Neptune pumps out more energy from its own interior than it receives from the distant Sun, a measured fact that overturns the assumption that solar input governs atmospheric intensity. The planet is generating its own heat from deep within its interior and releasing it into the atmosphere at a rate that far exceeds the solar contribution. This internal energy source is what powers the winds, drives the storms, fuels the cloud formation, and sustains the atmospheric violence that has no right to exist on a world this cold and this far from the Sun. But stating that Neptune has an internal heat source is not the same as explaining why that heat source produces the specific atmospheric phenomena observed. Jupiter and Saturn also radiate more heat than they receive, yet their wind speeds are lower than Neptune's. Uranus has roughly similar mass and composition to Neptune, but radiates almost no excess heat and has a correspondingly calmer atmosphere. The internal heat alone does not explain everything. Something about Neptune's specific combination of internal energy, atmospheric structure, and physical conditions translates a modest excess heat output into the most extreme wind regime in the solar system. Understanding how that translation works requires going deeper, below the clouds, below the wind layer, into the strange and poorly understood interior of a world that has been visited by human technology exactly once, for a few hours, more than 35 years ago. The engine that drives Neptune's violence hides in the dark, and reaching it means confronting some of the most challenging unsolved problems in planetary science. The answer lies somewhere inside a frozen furnace, 4.5 billion kilometers from the Sun. There is a question buried inside everything we have discussed so far, and it is a question that sounds simple but carries the weight of an entire unsolved problem in planetary physics. Where does the energy come from? Not the energy that lights Neptune's upper atmosphere with faint reflected sunlight. Not the energy that drives the photochemical reactions producing methane hazes and hydrocarbon smog. The question is about the energy that powers the fastest sustained winds on any planet in the solar system. The energy that builds Earth-sized storms out of frozen gases and then tears them apart within a few years. The energy that keeps an atmosphere screaming at over 1,000 miles per hour on a world that sits in near total darkness at the far edge of the planetary system. The Sun cannot be the answer. We have already established this with the numbers. Neptune receives roughly 1/900th of Earth's solar input. Even if Neptune's atmosphere were a perfectly efficient heat engine, converting every photon of incoming sunlight directly into kinetic energy with zero waste, which violates thermodynamics, the result would not come close to explaining the observed wind speeds. The solar energy budget at Neptune is simply too small to account for what the atmosphere is doing. by a factor of hundreds. The arithmetic does not work. The Sun is a spectator at this distance, not a driver. The answer, confirmed by direct measurement, comes from inside the planet itself. When Voyager 2 passed Neptune in August 1989, its infrared instruments measured the thermal radiation the planet emitted into space. Every object warmer than absolute zero emits thermal radiation, and the total amount radiated depends on the object's temperature and surface area. By measuring how much infrared energy Neptune was radiating across all wavelengths, scientists could calculate the planet's total thermal output and compare it to the total solar energy being absorbed. The result was unambiguous. Neptune radiates approximately 2.6 times more energy than it absorbs from the Sun. This means the planet is generating roughly 1.6 times its solar energy input from internal sources. The total internal heat flux is modest by stellar standards, roughly a few tenths of a watt per square meter, but it is more than sufficient to dominate Neptune's energy budget. The Sun contributes less than 40% of the total energy flowing through Neptune's atmosphere. The rest comes from within. This measurement transformed the entire framing of Neptune's atmospheric behavior. The winds, the storms, the dark spots, the dramatic cloud variability, none of these features need to be powered by sunlight. They are powered by heat rising from the planet's deep interior, energy that has been stored since Neptune's formation 4.5 billion years ago, slowly leaking outward through the atmosphere and driving the meteorological chaos observed at the cloud tops. But saying that Neptune has an internal heat source immediately raises a deeper question. What physical process generates that heat? And why does Neptune produce so much more excess heat than Uranus, a planet with almost identical mass, similar composition, and a comparable distance from the Sun? The most straightforward explanation for internal heat in giant planets is residual formation energy. When planets form through the accretion of gas and dust in a protoplanetary disk, the gravitational contraction of material releases enormous amounts of energy. Some of this energy radiates away during the formation process itself, but a significant fraction becomes trapped in the planet's interior, stored as thermal energy in the compressed materials of the core and mantle. Over billions of years, this trapped heat slowly conducts and convects outward through the planet's interior, eventually reaching the atmosphere and radiating into space. This process is called Kelvin-Helmholtz contraction, and it operates in all 4 giant planets to varying degrees. Jupiter and Saturn, being much more massive than Neptune, trapped far more formation energy and continue releasing it at significant rates. Jupiter's energy balance ratio of approximately 1.7 and Saturn's ratio of approximately 1.8 are well explained by this mechanism. The planets are still cooling from their formation, slowly contracting under their own gravity, and the gravitational potential energy released by this ongoing contraction supplements the original trapped heat. Neptune's energy balance ratio of approximately 2.6 fits comfortably within this framework in one sense. The planet formed from an enormous amount of material collapsing under gravity, trapped a substantial reservoir of thermal energy, and continues to release it over geological time. The numbers are consistent with standard models of planetary cooling for a body of Neptune's mass and age. But here is where the problem becomes acute. Uranus is Neptune's near twin. The 2 planets have similar masses, Uranus at roughly 14.5 Earth masses and Neptune at roughly 17. They have similar diameters, similar bulk compositions, and similar atmospheric structures dominated by hydrogen and helium over mantles of compressed ices. By every obvious metric, Uranus and Neptune should have similar internal heat budgets and similar atmospheric behaviors. They do not. Uranus radiates almost no excess heat. Its energy balance ratio is approximately 1.06, which is statistically indistinguishable from thermal equilibrium with the Sun. Uranus appears to have either lost its internal heat much faster than Neptune, or something is preventing that heat from reaching the atmosphere. The result is the atmospherically bland, meteorologically quiet world that Voyager 2 observed in 1986. Uranus looked dead precisely because it had no significant internal energy source to drive atmospheric motion. Neptune, by contrast, is alive, and the difference between the 2 planets remains one of the outstanding puzzles in planetary science. Several hypotheses have been proposed to explain the discrepancy. the most widely discussed, involves the extreme axial tilt of Uranus. Uranus rotates on its side with an axial tilt of approximately 98 degrees, meaning its poles alternately point almost directly at the Sun during its 84-year orbit. This unusual orientation is generally attributed to a massive collision early in the planet's history, an impact so violent that it knocked Uranus onto its side. Some researchers have proposed that this same collision disrupted the planet's internal heat transport by creating a stable thermal stratification that prevents efficient convection. In this model, Uranus's interior is still hot, but the heat is trapped beneath an insulating layer that blocks upward transport. The energy sits locked inside, unable to reach the atmosphere, leaving the outer layers cold and calm. Neptune, which has a more conventional axial tilt of approximately 28 degrees and presumably avoided such a catastrophic impact, retained efficient internal convection. Heat rises freely from its deep interior through the ice mantle and into the atmosphere, where it drives the extraordinary weather patterns observed. The difference is not in the total amount of internal heat, but in whether that heat can escape. Neptune lets its heat out. Uranus holds it in. This explanation is plausible but not fully confirmed. Alternative models suggest that differences in internal composition, perhaps varying ratios of water, methane and ammonia in the ice layers, could affect thermal conductivity and convective efficiency differently in the two planets. Others propose that Neptune may still be undergoing slow gravitational differentiation, with denser materials gradually sinking toward the core and releasing gravitational energy in the process. This ongoing settling would provide a continuous energy source beyond simple cooling from formation. Uranus, if its interior was more thoroughly mixed by the impact that tilted it, might have completed its differentiation earlier and exhausted this energy source. The honest answer is that we do not fully know why Neptune is so much more internally active than Uranus. The two planets present a natural experiment in planetary evolution, nearly identical starting conditions producing dramatically different outcomes, and resolving this puzzle will likely require dedicated orbital missions to both worlds, missions that are currently in the planning stages but remain decades away from launch. What we do know is that Neptune's internal heat, whatever its precise origin, is real, measured, and sufficient to drive everything we observe in the atmosphere. And the next question becomes, how does a relatively modest internal heat flux translate into the most extreme winds in the solar system? This is where Neptune's atmospheric physics becomes genuinely strange. The total internal energy flux at Neptune's cloud tops is small in absolute terms. We are talking about fractions of a watt per square meter, not the hundreds of watts per square meter that drive weather on Earth. By any naive accounting, this trickle of energy should produce gentle breezes at most. Certainly not supersonic jet streams, certainly not continent-sized vortices. The fact that it produces the most violent atmospheric circulation in the entire planetary system requires explanation, and the explanation reveals something counterintuitive about how atmospheres work on ice giants. The key lies in three interconnected factors that conspire to amplify Neptune's atmospheric energy into extreme velocity: the absence of a solid surface, the shallowness of the active wind layer, and the role of extreme cold in reducing atmospheric friction. First, the surface. Earth's atmosphere loses enormous amounts of kinetic energy through friction with the ground. Wind blowing over oceans, forests, mountains, and cities encounters constant drag that saps velocity. Hurricanes weaken rapidly when they make landfall precisely because the rough terrain disrupts their circulation and drains their energy. Jupiter and Saturn, being gas giants with no solid surfaces, avoid this energy loss entirely, which partially explains their powerful atmospheric dynamics. Neptune, likewise, has no solid surface anywhere near its visible atmosphere. The hydrogen-helium envelope transitions gradually into the dense, hot ice mantle deep below, but there is no abrupt boundary, no rocky crust, no ocean floor creating drag. The winds blow unimpeded across the entire planet, circling the globe without encountering any obstacle that might slow them down. Energy that enters the atmosphere as kinetic motion stays as kinetic motion, accumulating rather than dissipating. Second, the depth. Research into Neptune's atmospheric dynamics has revealed that the active wind layer is extraordinarily shallow, compared to the planet as a whole. The fast-moving jets and storm systems are confined to approximately the outermost 0.2% of Neptune's mass. In absolute terms, this corresponds to a layer roughly 600 to 1,100 kilometers deep at most. Below this layer, the atmosphere transitions into the dense interior, where conditions are so extreme that atmospheric dynamics as we understand them cease to apply. This shallowness has a profound consequence for wind speeds. Think of it in terms of energy efficiency. A given amount of thermal energy rising from the interior does not need to accelerate the entire atmosphere to produce fast winds. It only needs to accelerate a thin shell of relatively low-density gas at the very top of the planet. The mass of this shell is tiny compared to Neptune's total mass. Moving a small amount of gas very fast requires far less energy than moving a large amount of gas moderately fast. Neptune's atmosphere achieves extreme velocities precisely because the moving layer is so thin. The internal heat flux, modest though it is in absolute terms, is concentrated into accelerating a comparatively small mass of atmospheric gas, and the result is extraordinary speed. Third, and perhaps most counterintuitively, the extreme cold itself helps. Neptune's cloud top temperatures hover around -214 degrees Celsius. At these temperatures, the atmospheric gases have very low thermal energy, which translates into low viscosity. Viscosity is the internal friction within a fluid, the resistance of adjacent layers to sliding past each other. In a warm, dense atmosphere, viscosity acts as a brake on wind speeds, converting kinetic energy into heat through internal friction. In Neptune's frigid atmosphere, this internal friction is dramatically reduced. The cold gas offers almost no resistance to being moved. Once a parcel of atmosphere acquires velocity, it retains that velocity with minimal loss. The winds, having been accelerated by rising internal heat, simply keep going. There is no surface to stop them. There is almost no viscosity to slow them. The energy that enters the atmosphere stays in the atmosphere, building velocity over time until it reaches the extraordinary speeds observed. This trio of factors, no surface friction, a shallow active layer, and reduced viscosity from extreme cold, creates a kind of atmospheric flywheel effect. Energy from Neptune's interior enters the base of the wind layer as thermal convection. It is converted into kinetic energy as the gas accelerates, and then it persists, barely diminished, circling the planet in permanent high-speed flows. The system is astonishingly efficient at translating modest energy input into extreme atmospheric velocity. The result is paradoxical in a way that challenges everyday intuition. Less total energy can produce faster winds if the conditions are right. Neptune demonstrates that atmospheric violence is not simply proportional to the amount of energy available. It depends on how that energy is distributed, how efficiently the atmosphere converts it into motion, and how effectively the atmosphere retains kinetic energy once it is generated. Neptune's atmosphere is not powerful in the way that Jupiter's atmosphere is powerful, through sheer brute force of size and energy. It is powerful in the way that a precision instrument is powerful, channeling a small input into a concentrated, devastating output. To appreciate how unusual this efficiency is, consider the energy comparison in more concrete terms. Earth's atmosphere absorbs roughly 20 times more total energy from the Sun than Neptune's atmosphere receives from all sources combined, solar and internal. Earth uses that enormous energy budget to generate maximum sustained wind speeds of approximately 215 miles per hour in the most extreme tropical cyclones, events so powerful they cause catastrophic destruction across hundreds of kilometers. Neptune, with a total atmospheric energy budget roughly a 20th the size, generates sustained winds exceeding 1,300 miles per hour as a permanent, planet-wide feature rather than a localized extreme event. The ratio of wind speed to available energy on Neptune exceeds Earth's ratio by a factor so large it seems to violate intuition about how atmospheric physics should work. The resolution lies in understanding that wind speed is not a simple function of total energy input. It is a function of how energy is distributed within the atmosphere. On Earth, solar heating creates temperature gradients between the equator and the poles, between land and ocean, between day and night. These gradients drive atmospheric circulation, but they also create enormous amounts of turbulent mixing. Energy is constantly being transferred between different scales of motion, from planetary waves down to small eddies, and dissipated through friction with the surface, evaporation, precipitation, and radiation. The atmosphere is a leaky system. Most of the energy that enters it is lost to processes other than driving wind. Neptune's atmosphere is the opposite. It is the closest thing to a frictionless system that planetary science has observed. The energy entering the base of the wind layer has almost nowhere to go except into accelerating the gas. There is no surface to create drag. There is minimal turbulent dissipation because the extreme cold suppresses the small-scale instabilities that generate turbulence in warmer atmospheres. The energy cannot easily escape through radiation because the atmosphere is largely transparent at the wavelengths where thermal radiation would carry energy away from the wind layer. The result is an atmosphere that functions like a flywheel in a vacuum, accumulating kinetic energy over time because the loss mechanisms that would drain that energy in any warmer, more complex atmosphere are almost entirely absent. The winds reach extraordinary speeds not because the energy input is extraordinary, but because the energy retention is extraordinary. This understanding also helps explain why Uranus, despite having similar atmospheric composition and structure, is so much calmer. Without a significant internal heat source, Uranus lacks the energy input needed to sustain high-speed winds. Even though Uranus's atmosphere shares the same low-friction, no-surface characteristics as Neptune's, there is simply nothing driving the atmospheric machinery. The flywheel has no engine. The winds on Uranus are modest because the energy budget is modest. Neptune's engine runs hot enough, barely, to spin the flywheel to extraordinary speeds. Uranus's engine has essentially stalled. But the atmosphere is not the only domain where Neptune's internal activity manifests in surprising ways. In March 2025, a discovery was published in the journal Nature Astronomy that added an entirely new dimension to our understanding of Neptune's dynamic behavior. For the first time, the James Webb Space Telescope detected infrared auroras on Neptune, completing a 30-year search that had frustrated astronomers using every other available instrument. Auroras on giant planets are produced when charged particles, typically originating from the solar wind, become trapped in a planet's magnetic field and are funneled toward the magnetic poles. As these particles collide with atmospheric molecules, they transfer energy that ionizes the gas and produces characteristic emissions. On Jupiter, Saturn, and Uranus, auroras had been detected decades ago through their infrared signature, specifically through the emission of a molecule called the trihydrogen cation, a positively charged ion consisting of 3 hydrogen atoms. This molecule forms when energetic particles strike a hydrogen-dominated atmosphere, and its infrared emission lines serve as an unmistakable tracer of auroral activity. On Neptune, the trihydrogen cation had been predicted to exist but stubbornly refused to appear in any observation. Ground-based telescopes, including the Keck Observatory and the NASA Infrared Telescope Facility, had searched for it repeatedly without success. The non-detection was puzzling because models predicted that Neptune's magnetic field, which is both strong and extraordinarily tilted, should produce vigorous auroral activity. Neptune's magnetic field deserves particular attention because it is one of the most unusual in the solar system. On Earth, the magnetic field is roughly aligned with the planet's rotational axis, with the magnetic poles sitting near the geographic poles. Jupiter and Saturn have similarly well-aligned magnetic fields. Neptune breaks this pattern dramatically. Its magnetic field is tilted approximately 47 degrees from its rotational axis and is offset from the planet's center by a significant fraction of Neptune's radius. This means that Neptune's magnetic poles lie not near the geographic poles, but closer to the mid-latitudes, roughly where South America would sit on Earth. The field itself is thought to be generated not in a metallic hydrogen core like Jupiter's, but in the ionic water layer of Neptune's ice mantle, where extreme pressures dissociate water molecules and create an electrically conducting fluid capable of sustaining a dynamo. The JWST observations, obtained in June 2023 using the near-infrared spectrograph, finally broke the 3-decade drought. The data revealed an extremely prominent emission line corresponding to the trihydrogen cation, confirming its presence in Neptune's upper atmosphere for the first time. The infrared images showed auroral emission appearing as bright patches in Neptune's southern hemisphere, positioned exactly where the tilted magnetic field would funnel charged particles into the atmosphere. Neptune's auroras do not glow at the poles, as Earth's do. They glow at the mid-latitudes, a visible consequence of that wildly offset magnetic geometry. But the JWST data contained an additional surprise that deepened the mystery of Neptune's atmospheric behavior. The researchers measured the temperature of Neptune's upper atmosphere, the ionosphere, and found that it had cooled dramatically since the Voyager 2 era. In 1989, Voyager measured ionospheric temperatures of roughly 700 Kelvin. The JWST data from 2023 indicated temperatures of approximately 358 Kelvin, just over half of the Voyager value. Neptune's upper atmosphere had cooled by several hundred degrees over 3.5 decades. This finding was consistent with an independent study published in 2022 that had documented dramatic stratospheric cooling on Neptune, using 20 years of ground-based thermal infrared observations. Together, the results suggested that Neptune's upper atmosphere is far more variable than anyone had expected. A world at the outermost reach of the planetary system, receiving negligible solar heating, was nonetheless undergoing temperature swings of hundreds of degrees in its upper atmospheric layers over timescales of decades. The cooling also explained the 3 decades of failed aurora searches. Astronomers had been predicting the brightness of Neptune's auroras based on the temperature measured by Voyager 2. A hotter ionosphere produces stronger trihydrogen cation emission. When the ionosphere cooled to half its Voyager-era temperature, the auroral emission became correspondingly fainter, dropping below the detection threshold of every instrument except JWST. The auroras had likely been present throughout the intervening decades, but they were simply too dim to detect with the technology available. Only the extraordinary infrared sensitivity of the James Webb Space Telescope, the most powerful space observatory ever built, was capable of pulling the signal out of the noise. The aurora discovery matters for understanding Neptune's violence because it reveals the complexity of the planet's interaction with its space environment. The tilted offset magnetic field channels solar wind particles into the atmosphere at unusual latitudes, depositing energy in locations that would be unexpected on any other planet. This energy deposition contributes to ionospheric heating, drives chemical reactions, and influences the dynamics of the upper atmosphere in ways that are still being characterized. Neptune's magnetic field is not a passive structure. It is an active participant in the planet's atmospheric behavior, funneling external energy into the atmosphere in patterns dictated by its bizarre geometry. The geometry of Neptune's magnetic field deserves closer examination because it is among the strangest in the entire solar system, and it directly shapes how energy enters the planet's atmosphere. On Earth, the magnetic dipole axis is tilted approximately 11 degrees from the rotational axis, a modest offset that places the magnetic poles near the geographic poles. Jupiter's magnetic axis is tilted about 10 degrees. Saturn's is almost perfectly aligned with its rotation. These configurations produce auroral ovals centered near the poles, where solar wind particles are channeled downward along magnetic field lines that converge at high latitudes. Neptune's magnetic field breaks this pattern in 2 distinct ways. First, the dipole axis is tilted 47 degrees from the rotational axis, nearly halfway to the equator. Second, the dipole center is offset from the geometric center of the planet by roughly 0.55 of Neptune's radius. This means the magnetic field is not only tilted but displaced, creating a highly asymmetric magnetosphere where the field strength varies enormously across the planet's surface. At some locations, the magnetic field is several times stronger than at others. The result is an auroral pattern that shifts dramatically as Neptune rotates, sweeping the zones of particle precipitation across a wide range of latitudes rather than confining them to narrow polar caps. This wild magnetic geometry is thought to arise from the location where the field is generated. On Earth and Jupiter, the magnetic field originates deep in the planetary interior, in Earth's liquid iron outer core and Jupiter's metallic hydrogen layer. These dynamo regions sit close to the center of the planet, producing relatively symmetric dipole fields. On Neptune, the dynamo is believed to operate in the ionic water layer of the ice mantle, a region located much farther from the planet's center, at intermediate depths where water molecules are dissociated by extreme pressure into hydrogen and oxygen ions that flow as an electrically conducting fluid. Generating a magnetic field in this off-center, shell-like region naturally produces the tilted, offset dipole geometry observed. The auroral energy deposited into Neptune's atmosphere through this irregular magnetic funnel adds a supplementary heating source that is distributed asymmetrically across the planet. Unlike the relatively steady internal heat rising from below, auroral heating is concentrated, variable, and linked to conditions in the solar wind and the magnetosphere. The JWST observations captured the auroral emission at a specific moment in Neptune's rotational phase, providing a snapshot rather than a complete map. Future observations at different rotational longitudes will reveal how the auroral pattern evolves as the offset dipole sweeps through different orientations relative to the solar wind, potentially showing dramatic variations in auroral brightness and location on timescales of hours. The auroras also underscore a recurring theme in Neptune science. Every time a new instrument observes this planet with greater sensitivity or at different wavelengths, it reveals activity that was previously hidden. Voyager 2 discovered the winds and storms. Hubble revealed the life cycle of the dark spots. Ground-based telescopes documented the cloud disappearance. JWST found the auroras and the temperature variability. Neptune is not a world that gradually yields its secrets through incremental improvements in observation. It is a world that repeatedly ambushes scientists with phenomena they did not expect, revealing layers of complexity that grow with every new observation. And this brings us to a fact that sharpens everything we have discussed. Only one spacecraft has ever visited Neptune, a single flyby more than 35 years ago, and nearly everything we know about this planet's interior, its wind profiles, and its storm dynamics has been inferred remotely from billions of kilometers away. The details of what lies below the cloud tops, the exotic ice mantle, the dynamo region, the processes connecting the deep interior to the atmospheric violence above, remain largely beyond the reach of current observation. What lies beneath Neptune's visible atmosphere is a realm of physical conditions so extreme that they challenge our ability to simulate them, even in the most advanced laboratory experiments on Earth. Below the hydrogen-helium atmosphere, pressures increase rapidly with depth. Within a few thousand kilometers, conditions reach the point where the molecular hydrogen that dominates the upper atmosphere transitions into denser phases. But unlike Jupiter and Saturn, where hydrogen eventually reaches pressures sufficient to become metallic, Neptune's interior is dominated by a different set of materials entirely. Water, methane, and ammonia, the volatile ices that give Neptune its classification as an ice giant, exist under these conditions in states of matter that have no counterpart in everyday human experience. Water at pressures exceeding several hundred gigapascals and temperatures of several thousand degrees Kelvin is predicted to enter a phase called superionic ice. In this state, the oxygen atoms lock into a rigid crystalline lattice, while the hydrogen atoms detach from their parent molecules and flow freely through the lattice as bare protons, behaving like a liquid within a solid framework. Superionic water is simultaneously a solid and a liquid, depending on which atom you examine. It conducts electricity through the flow of hydrogen ions, making it an essential component of the dynamo process that generates Neptune's magnetic field. Laboratory experiments using laser-driven shock compression at facilities, including the Lawrence Livermore National Laboratory, have confirmed that superionic water exists at the pressures and temperatures expected inside Neptune, providing direct physical evidence that this exotic phase of matter plays a real role in the planet's interior dynamics. Methane under similar conditions behaves equally strangely. At pressures exceeding a few tens of gigapascals, methane molecules dissociate. The carbon atoms are squeezed out of their bonds with hydrogen and compressed into diamond crystals, while the liberated hydrogen rises upward through the interior. This process, sometimes described as diamond rain, means that Neptune's deep interior may contain a continuous precipitation of solid diamond crystals falling through a fluid of compressed volatiles toward the rocky core. The energy released by this precipitation, gravitational potential energy converted to heat as dense diamond sinks through lighter surrounding material, could represent a significant and ongoing contribution to Neptune's internal heat budget. If diamond rain is occurring, it provides a mechanism for continuous energy generation that goes beyond simple cooling from formation. The planet would be actively producing new heat through gravitational differentiation of its internal materials, supplementing the residual formation energy, and helping to explain why Neptune's internal heat flux has remained so vigorous after 4.5 billion years. The rocky core at the very center of Neptune is estimated at roughly 1 to 1.5 Earth masses, compressed to pressures exceeding 700 gigapascals, nearly 7 million times Earth's atmospheric pressure. The temperature at the core boundary is estimated at approximately 5,000 degrees Celsius, comparable to the surface of the Sun. This core is not a frozen relic at the bottom of a cold planet. It is a furnace, fan-shading energy outward through the exotic ice layers that surround it, driving the convective processes that transport heat to the atmosphere, and ultimately power the winds that circle the planet at record-breaking speeds. What this means is that the violence we have documented so far almost certainly represents only a fraction of Neptune's true atmospheric behavior. There are storms we have never seen because no telescope was looking at the right time. There are wind features at latitudes Voyager could not measure. There are chemical processes occurring beneath the cloud deck that no instrument has ever detected. The planet we think we know is a sketch drawn from glimpses, and the full portrait, when we finally obtain it, will likely be far more complex, far more dynamic, and far more violent than anything currently in the scientific literature. Neptune sits at the edge of the solar system, wrapped in its deceptive blue beauty, powered by an internal engine that no one fully understands, generating atmospheric violence that no simple model can explain. It is cold, dark, distant, and almost entirely unexplored, and it is raging. Pull back now. Leave the cloud tops. Leave the wind measurements and the infrared spectra and the dark spot tracking data. Rise above Neptune until the planet shrinks to a blue point, then shrink it further until it becomes just another dot in the arrangement of worlds orbiting an ordinary star. See the solar system as a structure, Mercury baking in the inner furnace, Venus choking under its greenhouse shroud, Earth, green and blue and improbably alive, Mars, rusted and cold and almost still, then the gap, the asteroid belt, the rubble of a planet that never formed. Beyond it, the giants. Jupiter, the Colossus, wrapped in bands of ammonia cloud, its great red spot grinding away century after century. Saturn, elegant behind its rings, its hexagonal polar vortex spinning with geometric precision. Uranus, tilted on its side, pale blue-green, quiet. And then, at the far edge, 30 times farther from the Sun than Earth, there is Neptune. From this distance, Neptune looks like the ending of a story, the final note in a composition that has been winding down for billions of kilometers. The solar system begins with fire and fury close to the Sun, and it should end with ice and silence at the outer boundary. Every planet farther from the Sun is colder than the one before it. Every step outward reduces the available energy. The narrative arc of the solar system, read from the inside out, is a story of diminishing intensity, decreasing drama, and increasing stillness. Neptune should be the quietest chapter, the epilogue, the world where the last traces of solar influence finally fade to nothing and the atmosphere settles into permanent frozen equilibrium. We now know that this reading of the solar system is wrong, not slightly wrong, not wrong in the details while correct in the broad strokes, wrong in its fundamental assumption, the assumption that distance from the Sun determines atmospheric intensity, the assumption that cold worlds should be calm worlds, the assumption that the outermost giant planet should be the least meteorologically interesting object among its peers. Neptune violates every one of these assumptions so thoroughly that the violation itself becomes the defining fact about the planet. Consider what we have established so far. Neptune holds the record for the fastest sustained winds ever measured on any planet. Its equatorial jet screams retrograde, while higher latitude flows race prograde at velocities that dwarf anything Jupiter or Saturn produces, despite both those worlds being closer to the Sun, far more massive, and incomparably better supplied with energy. Not Jupiter, with its 318 Earth masses and its relatively generous solar energy budget. Not Saturn, with its spectacular ring system and its massive periodic storm eruptions. Neptune, the smallest giant, the farthest giant, the coldest giant, the one receiving a vanishingly small share of the Sun's total output. That is the planet holding the wind speed record. Neptune generates dark vortex storms rivaling Earth in size, sustains them for years, and then destroys them entirely, only to generate new ones in different hemispheres. Jupiter's Great Red Spot has been stable for centuries. Neptune's equivalent features have lifetimes measured in years. The atmosphere cycles through periods of intense storminess and relative calm, with a cadence that suggests continuous internal generation of atmospheric violence, balanced against dissipation mechanisms that prevent any single storm from achieving permanence. The atmosphere is not just violent, it is violently unstable, a system in constant flux, generating and consuming its own features in a rhythm that no other giant planet exhibits. Neptune's cloud cover can transform dramatically within months, driven by photochemical responses to solar ultraviolet variations so faint they should be undetectable at that distance. The entire visible appearance of the planet changed between 2019 and 2020, shifting from a world decorated with bright methane cloud bands to a nearly featureless blue sphere stripped of its atmospheric ornamentation. Even the Sun, reduced to a pale point of light 4.5 billion kilometers away, retains enough influence to trigger photochemistry in Neptune's upper atmosphere, and Neptune's atmosphere is responsive enough to translate that feeble input into planetary-scale transformations. And beneath all of this, the engine, Neptune radiates far more energy than it absorbs from the Sun, with the internal contribution dominating the planet's total energy budget. The internal heat source, likely residual energy from formation supplemented by ongoing gravitational processes, dominates the planet's energy budget and powers the atmospheric violence that no amount of solar input could sustain. The heat rises through the compressed ice mantle, enters the base of the thin atmospheric shell, and drives the convective machinery that accelerates the winds to their record-breaking velocities. The atmosphere, lacking any solid surface to create friction and operating at temperatures so low that internal viscosity nearly vanishes, converts this modest energy input into extreme kinetic output with an efficiency that borders on the surreal. Now hold all of this in your mind and place it beside the other giant planets. Jupiter is the obvious point of comparison because Jupiter is the archetype of atmospheric violence in the solar system. The Great Red Spot alone has become a cultural symbol of planetary weather at its most dramatic. Jupiter's atmosphere features dozens of alternating cloud bands, massive lightning storms, and turbulent vortex interactions that have been studied continuously for centuries through telescopes and for decades through spacecraft. Jupiter is a violent world by any measure, but Jupiter's violence makes sense. Jupiter is by far the most massive planet, containing more mass than all other solar system planets combined. Its enormous gravitational compression generates substantial internal heat, and its relative proximity to the Sun, 5 times Earth's distance rather than 30, provides meaningful solar input on top of that internal energy. Jupiter has the mass, the energy, and the atmospheric depth to support every feature observed in its atmosphere. The Great Red Spot persists because Jupiter's atmosphere is massive enough and energetic enough to sustain a stable vortex for centuries. The cloud bands persist because Jupiter's powerful Coriolis forces, driven by a rotation period of less than 10 hours in a planet 140,000 kilometers across, organize the atmospheric flows into narrow, stable jets. Everything about Jupiter's weather follows from Jupiter's physical properties in ways that, while complex in detail, are intuitive in outline. Big planet, lots of energy, spectacular weather. The logic holds. Saturn is similar, slightly less massive, slightly farther from the Sun, slightly calmer in its normal state, but capable of producing enormous periodic storms that erupt roughly once every 30 years and can encircle the entire planet in bands of white cloud and electrical activity. Saturn's storm behavior is episodic rather than continuous, but when the storms come, they are immense. Again, the violence is proportional to the resources available. Saturn is a large, warm, internally heated world with more than enough energy to drive periodic atmospheric explosions. Uranus provides the negative control. Similar in mass and composition to Neptune, but lacking significant internal heat, Uranus presented Voyager 2 with an almost featureless atmosphere in 1986. Subsequent observations have revealed that Uranus does have weather, including cloud features and occasional bright storms, but the activity is muted compared to Neptune, consistent with the dramatically lower energy budget. Uranus demonstrates what happens when an ice giant lacks the internal engine. The atmosphere exists, the composition is similar, the physical conditions are comparable, but the driving force is absent. The result is a world that behaves approximately as expected for a cold, distant, energy-starved planet. Neptune breaks the pattern. It is smaller than Jupiter and Saturn. It is farther from the Sun than any of them. It receives less solar energy than any of them. It is colder than any of them. On every superficial metric, Neptune should fall somewhere between Uranus and Saturn on the scale of atmospheric activity, perhaps slightly more energetic than Uranus thanks to its greater internal heat, but certainly less dramatic than the massive, sun-warmed gas giants closer in. Instead, Neptune matches or exceeds their atmospheric violence in key respects. Its wind speeds surpass Jupiter's. Its storm generation rate exceeds anything observed on the other giants. Its atmospheric variability, as measured by the cycling of dark spots and the dramatic disappearance and reappearance of cloud cover, is unmatched among the giant planets. This is the fact that makes Neptune genuinely unsettling rather than merely interesting. It is not simply that Neptune has weather. It is that Neptune has weather this extreme, despite having every reason not to. The violence is disproportionate. It is excessive. It exceeds what the available energy should be able to produce, and it exceeds what the planet's modest size and extreme distance should permit. Neptune does not merely defy the expectation that the farthest giant should be the calmest. It inverts the hierarchy entirely, placing the smallest, coldest, most distant giant at the top of the atmospheric violence ranking. And this inversion carries implications that extend well beyond Neptune itself. For most of the history of planetary science, the unspoken assumption has been that atmospheric activity scales with available energy. More sunlight means more weather. Closer to the star means more dynamic. This assumption informed predictions about every planet before it was visited, and it was largely confirmed by observations of Mercury, Venus, Earth, Mars, Jupiter, and Saturn. The progression made sense. The solar system appeared to be organized according to a simple gradient where stellar proximity equaled atmospheric intensity. Neptune reveals that this gradient is an oversimplification. It is not wrong for the inner solar system, where solar energy genuinely dominates atmospheric dynamics, but it breaks down catastrophically in the outer solar system, where internal planetary energy can overwhelm the solar contribution by factors of 2 or 3. Neptune demonstrates that a planet's atmospheric behavior is not determined by its position relative to its star alone. It is determined by the interplay between external energy input and internal energy production, modulated by atmospheric structure, composition, and physical conditions that can amplify modest energy sources into extreme atmospheric phenomena. This insight has profound consequences for how we think about planets beyond our solar system. Exoplanet science has discovered thousands of worlds orbiting other stars, and a significant fraction of them are Neptune-sized, or Neptune-mass planets, orbiting at various distances. Some of these worlds sit in tight orbits close to their host stars, blasted by intense radiation. Others orbit at enormous distances where stellar input is negligible. The conventional assumption would be that the distant ones should be atmospherically quiet, while the close-in ones should be active. Neptune tells us that this assumption may be dangerously wrong. A Neptune-mass planet orbiting far from its star could still possess a vigorous internal heat source. It could still have a shallow, low-friction atmosphere capable of translating modest energy into extreme wind speeds. It could still be violent, even in the dark. We cannot see the atmospheres of most exoplanets in any detail yet, but when we can, Neptune suggests that we should prepare for surprises. The quiet worlds may turn out to be raging. The distant, cold planets may turn out to have the most extreme atmospheric dynamics. The universe may not organize its weather according to the tidy gradient that the inner solar system suggests. There is another dimension to Neptune's significance that deserves attention, and it concerns how little we actually know about this world despite everything we have discussed. Every fact presented in this story, every wind speed, every storm observation, every temperature measurement, rests on an astonishingly thin foundation of direct data. One spacecraft, Voyager 2, has visited Neptune, and it spent only a few hours in close proximity during its flyby on the 25th of August, 1989. The encounter was planned primarily to study Triton, Neptune's large captured moon, and the atmospheric observations, while revolutionary, were limited to what could be captured during a single rapid pass. Voyager 2 observed Neptune from one angle at one moment in the planet's 165-year orbit, with instruments designed and built in the 1970s. Everything else we know about Neptune has been obtained from a distance of more than 4 billion kilometers using the Hubble Space Telescope, ground-based observatories, and most recently the James Webb Space Telescope. These instruments have provided extraordinary data given the limitations of remote observation, but they cannot substitute for the kind of sustained, close-up investigation that orbital missions provide. Jupiter has been studied by 6 dedicated spacecraft, including the Galileo orbiter that spent 8 years in the Jovian system and the Juno orbiter that continues operating today. Saturn was studied by the Cassini orbiter for 13 years. These missions transformed our understanding of those planets in ways that brief flybys never could. Neptune has received nothing comparable. No orbiter, no atmospheric probe, no long-duration mission of any kind. The proposed concepts for dedicated Neptune missions, including the Neptune Odyssey mission concept studied by NASA and the ice giant mission priorities identified in the most recent Planetary Science Decadal Survey, remain in the early planning stages. Even under optimistic timelines, a Neptune orbiter would not arrive at the planet until the 2040s or later, more than 50 years after Voyager 2's flyby. But what such a mission would reveal is almost beyond calculation. An orbiter circling Neptune for years rather than racing past in hours would track dark spots from birth to death in real time, capturing the formation, migration, reversal, fragmentation, and dissipation processes that Hubble can only sample in snapshots taken months apart. It would measure wind speeds at every latitude and altitude, building a 3-dimensional map of the atmospheric circulation that Voyager 2 could only sketch in 2 dimensions from a single vantage point. An atmospheric entry probe, if included, would descend below the cloud tops for the first time in history, directly measuring the temperature, pressure, composition, and wind speeds at depths no remote observation can reach, answering questions about what drives the storms at their source, rather than merely observing their surface expressions. The orbiter's gravity field measurements would map the distribution of mass inside Neptune with enough precision to determine whether the interior is fully differentiated or partially mixed, directly testing the models that attempt to explain why Neptune retains so much more internal heat than Uranus. And the magnetometer would track the evolution of that wildly tilted, offset magnetic field over months and years, revealing whether the dynamo in the ionic water layer fluctuates on short timescales or maintains a stable configuration despite its extraordinary asymmetry. Every instrument on such a mission would rewrite a chapter of Neptune science. Collectively, they would answer questions that have lingered unanswered since Voyager 2 disappeared into the outer dark. This means that the Neptune we think we know is a planet glimpsed through fragmentary observations spread across 35 years. The dark spots have been tracked intermittently. The wind profiles have been measured at a limited number of latitudes. The internal structure has been inferred from remote data and theoretical models. The atmospheric composition below the visible cloud tops remains almost entirely unknown. The exotic phases of water and ammonia in the ice mantle, the precise mechanism generating the magnetic field, the detailed vertical structure of the storm systems, the chemical reactions occurring in the deep atmosphere where pressures exceed millions of times, Earth's surface pressure, all of this remains terra incognita. We are studying one of the most violent planetary atmospheres in the solar system through the equivalent of a telescope pressed against a foggy window from the far side of a continent. The implication is that the violence we have documented is almost certainly incomplete. There are storms we have not seen. There are atmospheric processes we have not detected. There are interactions between the deep interior and the visible atmosphere that we have not characterized. The JWST aurora discovery was a vivid reminder of this. For 30 years, scientists searched for Neptune's auroras and found nothing. The auroras were there the entire time, hidden by a dramatic cooling of the upper atmosphere that no one had predicted. When the right instrument finally looked, The signal was unmistakable. How many other Neptunian phenomena are hiding in plain sight, waiting for the right instrument, the right wavelength, the right moment? The honest scientific assessment is that Neptune holds more surprises than any other major planet in the solar system. Not because Neptune is inherently more mysterious than other worlds, but because we have invested less observational effort in understanding it than in understanding any other giant planet. The ratio of atmospheric complexity to observational coverage is maximally unfavorable. We know enough to recognize that Neptune is extraordinary. We do not know enough to explain why. And this is perhaps the most unsettling aspect of Neptune's violence. It is not merely that the planet defies expectations. It is that the planet defies expectations in ways we do not fully understand, using mechanisms we cannot completely characterize, powered by energy sources whose origins remain debated, in an atmosphere whose deep structure has never been directly measured. The violence is real, the explanation is incomplete, and the gap between observation and understanding is wider for Neptune than for any other major planet. Step back one final time and look at Neptune not as a collection of wind speeds and storm statistics, but as an idea, as a concept about what the outer solar system actually is. For most of human history, the edge of the planetary system was imagined as a place of quietude. The ancients saw the wandering stars as celestial bodies moving through the heavens in stately, ordered paths. The Copernican revolution revealed those wandering stars as planets orbiting the sun, but the sense of cosmic order persisted. Closer planets moved faster, farther planets moved slower. The outer solar system was the domain of slow, cold, majestic worlds drifting through the darkness at the pace of geological ages. Even after the discovery of Jupiter's storms and Saturn's rings, the outermost planets retained an aura of frozen tranquility. Uranus reinforced this impression with its bland, featureless face. The edge of the solar system was supposed to be the place where everything wound down, where the sun's influence faded to nothing, and where the planets settled into the deep, permanent stillness of cosmic winter. Neptune destroys this idea, not gently, not partially, completely. The farthest major planet from the sun is not still. It is not calm. It is not the peaceful conclusion to the solar system's story of diminishing activity. It is one of the most dynamically violent worlds in the entire planetary system, a place where winds rage at speeds no other planet can match, where storms the size of Earth form and die within a handful of years, where the entire cloud structure can vanish and reassemble in response to the faintest solar whisper, and where an internal engine no one fully understands pumps energy into the atmosphere with relentless, continuous force. The real shock of Neptune is not that it has strong winds. It is not that it has big storms. It is that one of the coldest, darkest, most isolated major worlds in the solar system is still physically raging 4.5 billion years after it formed. The violence has not subsided. The engine has not cooled. The atmosphere has not settled. After billions of years in near-total darkness, receiving almost no external energy, Neptune is still fighting, still churning, still tearing itself apart and rebuilding with a ferocity that makes the sunny, warm, energy-rich inner solar system look tame by comparison. This is what makes Neptune more than a curiosity. It is a rebuke to the human tendency to assume that distance means safety, that cold means calm, and that the far edge of anything must be the place where intensity gives way to peace. The universe does not operate according to our comfort. It does not grade its violence on a curve that decreases with distance. It places one of its most aggressive planetary atmospheres at the farthest outpost in the coldest conditions, under the dimmest light, and lets it rage without apology and without explanation sufficient to satisfy the scientists who study it. Neptune is beautiful. Its blue is deeper and richer than any other planet's, a colour born from methane and mystery that photographs with an elegance that belies the chaos beneath. From a distance, it looks like a jewel, a sapphire set against the black velvet of deep space, the most serene object in the outer solar system. But the serenity is a mask. Beneath the blue, the winds howl, the storms boil, the vortices spin and shatter. The atmosphere screams across the planet, at velocities that would shred any structure humanity has ever built. The engine in the interior pumps heat upward with mechanical persistence, powering the violence year after year, century after century, epoch after epoch, long after the feeble sunlight at that distance has given up any pretense of influencing what happens on this world. The farthest major giant is not the quiet end of the solar system. It is one of its most physically aggressive worlds. And the only thing more unsettling than the violence itself is the knowledge that after 35 years and one brief flyby, we have almost certainly seen only a fraction of what Neptune is truly capable of doing. The storm is still out there. It has been out there since the solar system was young, and it is not slowing down.